Welcome to ThirdEye Labs, where we make the unseen seen. In the last episode, we met the function, the machine at the heart of all of AI. But to read what those machines do, we first have to read their language, mathematical notation. Today, we make the scary symbols simple. Here is the secret. Notation is not hard math. It is compressed shorthand, like emoji for ideas. Once you know what each symbol stands for, the wall of symbols becomes a short, readable sentence. First, the big one. This is sigma, the Greek letter S, and it simply means add things up. The number below says where to start, I equals 1. The number on top says where to stop, 4. And x sub I is the thing we add at each step. So let us unroll it. Sigma from 1 to 4 of x sub I is nothing more than x1 plus x2 plus x3 plus x4. That is it. It is a for loop that keeps a running total. On the right, the exact same idea written as code. And here is why you will see sigma everywhere in machine learning. Sigma w sub I, x sub I, is a weighted sum, the single most common operation inside a neural network. You already understand it. Multiply each input by its weight, then add them all up. Sigma has a twin, the capital Greek letter pi. It looks similar, but instead of adding, it multiplies. Pi from 1 to 4 of x sub I means x1 times x2 times x3 times x4. Same loop, just times instead of plus. You will meet it when probabilities combine, like the chance that several independent events all happen. Next, the little numbers stuck to a letter. A subscript like x sub 3 is just an index. It points to the third item in a list. Think of it as the address of one entry. A superscript can be trickier. Sometimes it is a power like x squared. But in machine learning, a superscript in brackets, like capital W with a 2 in brackets, is usually just a label. It means the weights of layer 2. It is naming, not exponentiation. Context tells you which. This often trips people up. X squared means multiply x by itself, but x with a bracketed 2 usually means the second version of x, a layer or a step. Same height on the page, completely different meaning. Now a symbol that scares people. The curly d, called partial. A straight d, as in df over dx, is the ordinary derivative, how the output changes when its single input changes. We saw functions of one input last time, but real models have many inputs at once. The curly d, partial f over partial x, asks a focused question: how does the output change if we wiggle just x, while holding every other input perfectly still? That is the only difference. Partial means hold everything else fixed. Quick example. Take f equals x squared plus 3y. Partial with respect to x. Treat y as a frozen constant, so the answer is 2x. Partial with respect to y. Treat x as frozen, so the answer is just 3. Each partial looks at one dial at a time. Now we can decode the upside-down triangle, called Nabla, or simply gradient. It looks exotic, but it is just a tidy way to collect all the partials into one list. Nabla f is the vector of every partial derivative, one slope per input, and it has a beautiful meaning. The gradient points in the direction where the function climbs fastest, straight uphill. Flip it around, and you are heading downhill. That single idea, follow the gradient downhill, is how almost every AI model learns. We will build it for real in a future episode. Finally, the small grammar words that glue equations together. The rounded E means is in or belongs to a set. The upside down A means for all. The backwards E means there exists. The wavy equals means approximately equal. And this last one means is proportional to. Learn these 5, and you can read the structure of almost any formula. Read together, x sub I is in the real numbers for all I simply says, every x in our list is a real number. A whole sentence in 5 symbols. 3 more symbols carry enormous weight in machine learning. First, the integral, this tall stretched s. If sigma adds up a finite list, the integral does the same thing for a smooth, continuous range. It is just a sum with infinitely many tiny pieces. You will see it all through probability. Second, the Blackboard E, called expectation. E of x just means the average value of x, the result you would expect on average over many tries. Almost every loss in machine learning is secretly an expectation, the average error over your data. Third, and maybe the most important of all, argmin and its twin argmax. Min would give the smallest value of the loss, but argmin asks a different question. Which input, which setting of the parameters theta produces that smallest value? That is the entire goal of training, written in one symbol. Find the parameters that make the loss as small as possible. Quick lightning round of 6 you will bump into constantly. Double bars around a vector mean its length, called the norm. A capital T in the corner means transpose. Flip the rows and columns of a matrix. The circled dot means multiply two list element by element. The wavy line, x tilde p, means x is drawn from a probability distribution. Single bars mean absolute value, the size of a number, ignoring its sign. And the sideways 8 is infinity, growing without bound. Notice what just happened. We never did any hard math. We only learned what each piece of shorthand stands for. That is the whole game. Open almost any paper and the first thing you meet is a Blackboard letter. Blackboard R means the real numbers, ordinary decimals. Blackboard N is the counting numbers, and Blackboard Z is the integers. But the real trick is the little exponent. It tells you the shape. R to the N is a vector of n real numbers. R to the m by n is a matrix with m rows and n columns. So when you read x is in R to the n, you instantly know x is a list of n numbers. For example, x is in R to the 784 simply says, x is an image flattened into 784 numbers. The notation told you the shape before you read a single word. Research papers are written in Greek, and each letter has a conventional job. Theta almost always means the parameters, the dials we are learning. Eta is the learning rate, how big a step we take. Lambda controls regularization, how much we penalize complexity. Gamma is the discount factor in reinforcement learning. Mu is a mean, sigma a standard deviation. Alpha and beta are usually tunable coefficients, and epsilon is a tiny number, often a little noise, or a guard against dividing by zero. Knowing these job titles lets you guess what an equation is doing at a glance. Probability has its own shorthand, and one symbol matters most, the vertical bar. P of y given x, written with a bar, means the probability of y given that x already happened. The bar is the word given. Almost every classifier outputs exactly this, the probability of a label given an input. Next, the script n, which stands for the normal distribution, the famous bell curve. X tilde script n of mu, sigma squared, reads, x is drawn from a bell curve centered at mu with spread sigma. This single object is everywhere in machine learning. Two more you will see constantly. DKL of P and Q is the KL divergence, a measure of how far apart two probability distributions are. It hides inside the cross-entropy loss. And ID, means the data points are independent and identically distributed, drawn fairly from the same source. It is the assumption almost every method quietly relies on. In linear algebra, typography carries meaning. A bold lowercase letter is usually a vector, a whole list of numbers, while a plain letter is a single number, a scalar. Capital letters are usually matrices. This convention alone removes half the confusion in a paper. A few more you will lean on. A transpose B, also written with angle brackets, is the inner or dot product. It collapses two vectors into one number measuring how aligned they are. We will explore this deeply in Season 1. Trace of a adds up the diagonal. Determinant of a measures how much a matrix scales volume. And capital I is the identity matrix, the do-nothing transformation. And a final grab bag that rounds out almost any paper. Colon equals means is defined as introducing a new name rather than stating an equation. The Blackboard one in brackets is the indicator. It equals 1 when the condition inside is true, and 0 otherwise. Big O of something describes how an algorithm's cost grows as the data grows. The small circle is composition. F circle G means do G first, then F. Exactly the machines feeding machines from episode 1. And the star is convolution, the sliding multiply and add at the heart of convolutional networks and of the Fourier transform. Let us decode a real formula you will meet on day 1 of machine learning, the mean squared error. A moment ago this would have looked like a wall. Now watch it dissolve into plain English. Y sub I, in green, is the true answer for example I. Y hat sub I, in blue, is what the model predicted. We subtract them to get the error, then square it, so negatives and positives do not cancel. The sigma, in yellow, adds that squared error over every example. 1 over n, in front, turns the total into an average. And the whole thing equals L, a single number measuring how wrong the model is. Decode the symbols, and the wall becomes one clear sentence, the average squared difference between prediction and truth. Let us bring it all together. Sigma adds, pi multiplies, and the integral sums over a continuous range. Subscripts are indices, bracketed superscripts are labels. The curly D holds everything else fixed, and Nabla gathers all the slopes into one uphill pointing vector. Blackboard E is an average, and argmin is the goal of training itself. Blackboard R with an exponent tells you the shape, and Greek letters carry fixed jobs. Theta for parameters, eta for the learning rate, lambda for regularization. The bar means given, the script n is the bell curve, and bold means a vector. Add the norms, transposes, and grammar symbols, and you can now read the structure of almost any machine learning paper. None of it was hard math. It was all just compression. Thanks for watching, and keep exploring. Next time, we tackle exponentials and logarithms, the math of growth that powers probability and loss. Please like and subscribe ThirdEye Labs if you enjoyed this video, and let me know in the comments.